class. Let's get going on the day 3 homework, and then that'll get us ready for our quiz, which is coming up. So here's the last day of the homework. Taking a look, this is one of our basic parent functions, a cube root function. So to sketch that should be pretty easy. There's no transformations even, so you might even have the shape of this thing memorized. But if you don't, you could just plot some points. I'm going to build a grid. Let's work from thinking you don't know the shape of this graph already. And just build a t-chart of x and y values. I don't know. There's always somebody who doesn't know why it's called a t-chart. It's called a t-chart because it makes the letter T. That's all we mean when we say a t-chart. So anyway, I would almost always want to evaluate at 0 first. Cube root of 0 is 0, so we know the graph passes through the origin. And then just go to 1. Cube root of 1 is 1. From there, try to pick values that make sense. 2, 3, 4, 5, 6, 7 all have ugly cube roots, but 8 has a cube root of 2. So, you know, kind of work intelligently that way. So 1 gives 1, but then we have to go all the way out to 8. So 1, 2, 3, 4, 5, 6, 7, 8. Just to get to a height of 2. We'd have to go all the way out to 27 just to get to a height of 3. So we can see we've got this really, really slow growth going on. But it's not asymptotic. There's no horizontal asymptote. We do grow forever and ever. We just grow really, really, really slowly. So what's happening on the left-hand side? Same thing. -1 has a cube root of -1. You can plot that point. -8 has a cube root of -2. You can plot that point. 1, 2, 3, 4, 5, 6, 7, 8. So by looking at the data in the table, we can see numerically that we are an odd function, right? +1 is giving +1, but -1 is giving the opposite of that. It's giving -1. That's happening for every possible input. On the graph, we can see that we've got that symmetry about the origin, which you can think of either as a 180-degree rotation around the origin, makes the two halves line up, or a reflection over y, and then also a reflection over x, makes the two halves line up. But this is what odd symmetry looks like, both numerically and graphically. And I guess while my train of thought is at this particular station, what does the odd symmetry look like algebraically? Well, you'd grab your function, which is the cube root function, and you would figure out what f of -x is. And like I said in the previous video, if you plug in -x, oh, I put a 3 there, my bad. If you plug in the -x and somehow the graph remains unchanged because the negative just kind of cancels out, then you're even because f of -x is exactly the same as the original function. But if you end up with the exact opposite of the original function, if you're able to factor a negative out to the front and just have negative parentheses the whole original function, then you know you're odd. And that's what will happen here. And if you were going to show me that work, I would still do that trick where I express the negative as essentially -1 that we're multiplying by. And then with any radical, whether it's a cube root, fourth root, even or odd, doesn't matter, you are allowed to break those radicals down over multiplication. So this becomes the cube root of just the -1 multiplied by the cube root of x. And then the cube root of -1, that's just a constant that we can evaluate. So we just evaluate it. We get -1 times the cube root of x. And then we've smoothly and unambiguously proven that, yeah, what we've got is the opposite of cube root of x, meaning we've got the opposite of f of x. And we've done it. We've shown that f of -x is the opposite of f of x. So we can say, therefore, f of x is odd. So there you go. So really quickly, there's a glimpse at all 3 representations of an odd function. Here we see the algebra proves that we're odd. In the graph, the geometry of the graph proves that we're odd. And in the table, just the numbers, right? Numerically, we see that odd behavior. All right, and then for the rest of this, The properties, once you've got a graph to look at, are pretty simple. Our domain is going to be all real numbers because, again, there's no division to give us division by 0. There's no... Oh, I lied. There is a radical. I was going to say there's no radical. But it's an odd radical. So odd radicals don't care, right? If you plug in negative inputs. So nothing to worry about there. And there's no other special function. Logarithms have natural domains. No, logarithms won't accept negatives. Some trigonometric functions have restrictions. Tangent, for example, has restrictions. But there's none of that. We can see that this is kind of a straightforward function whose domain would be all reals. The range is also going to be all reals. In terms of boundedness, if you look too quickly, you might think that this thing is bounded because you'd assume these are asymptotes, but they're not. It's just really slow growth. So this should be not bounded. And we do see the graph increases over its entire domain. So our increasing interval is going to be from negative infinity to infinity. Decreasing is none. The extrema are going to be a little boring. I don't see any global or local maxes or mins. So extrema, we're going to say none and none. And again, we're not doing Leb and Reb until the next assessment. So that's it for this guy. Those are all your properties. Moving on. I guess I forgot. We are supposed to be naming the function. This is a cube root. I'm sure I said that at some point. Okay, so to number 8. So for number 8, we get to our first rational function. And a rational function is any function of the form f of x equals some fraction where the numerator is a function in its own right and the denominator is a function in its own right. And if we went all the way back to number 1, it was what? I don't care what it was. I'm going to say x plus 2. I think it was minus 2, but it was all over 3. This looks like a function, but the denominator can't be a constant. The denominator has to be at least linear to have a rational function. Because again, when the denominator is a constant, we saw in number 1 that we just express this as fractions that are coefficients. And we saw this was just linear, right? 1/3 was our slope, 2/3 was our y-intercept. It was definitely minus. I'm totally certain of that now. Not that it matters. But there you go. That's the definition of a rational function. I should say the numerator and denominator also are supposed to be kind of simple, rational, polynomial. It's supposed to be polynomial functions. So the numerator can be a constant. The numerator can just be the number 1, but the denominator has to be at least linear to qualify. And then of course things get much more complicated when these things grow to be quadratic or cubic or even higher order. Then the graphs can become very, very complicated. But that's what a rational function is. And this is our first one. To find the domain of a rational function is pretty simple. The domain of a rational function is always going to be all real numbers except the values that make the denominator equal to 0. So we know this guy's domain will be all real numbers except, I like to use that little set subtraction sign, which is this little slash. And then inside of this symbol, which is called braces, you just write all the values of x that make the denominator 0. Those are called the zeros, by the way. So if I talk about the zeros, those are any values of x that make the denominator 0. So -1 is clearly out. And you should know, when you're graphing, the zeros of the denominator, they can be vertical asymptotes, but they also can be holes. So you might remember that from last year. Some graphs just have holes in them. And the difference there is a vertical asymptote is called an infinite discontinuity, and a hole is called a removable discontinuity. And certainly in the next couple of weeks, we'll see plenty of both of those things. We'll see all kinds of discontinuities. So what have we figured out? Not much. We figured out that at -1, we've got a vertical asymptote. Okay. Rational functions, at least simple ones like this, where the numerator and denominator are both linear, and I know this isn't exactly linear, it's a constant function, but that's a horizontal line, so I think it's fair to call it linear. But there's a rule that says when the denominator has the greater degree, you automatically get a horizontal asymptote at y equals 0. And maybe you know that rule from Algebra 2. Maybe someone in class can tell me, hey, Mr. F, you were right. We do know that rule. Or no, Mr. F, we've never heard that before. But we should have a horizontal asymptote here at 0. And then from here, the graph is going to be a hyperbola. Maybe you remember that word. You should have learned about hyperbolas in geometry. In geometry, when you learned about them, you graph them by finding their center, going up and down, and left and right to build this little box thing. You'd make a little rectangle, and the diagonals of the rectangle dictated the asymptotes. I wonder how many of you guys remember that. And then from there you could figure out, based on which variable came first in the equation, whether you had a branch that opened up and down or whether you had branches that opened left to right. But you could sketch in the midpoints of the rectangle were your vertices, and then the asymptotes shaped your graph. But that was one way to get a hyperbola. But there's nothing that says these asymptotes have to be diagonal. The asymptotes could be vertical. And that's what we get here, vertical and horizontal. And that shape is still called a hyperbola. So I'm going to take this away, huck it in the garbage. All right, so the question is, where does my graph live? Am I going to get a branch down here in quadrant 3 and 1, so to speak, or 2 and 4, so to speak? And if you have no idea, then the easiest thing to do is plot a couple points and find out. We can just plug in 0. That seems easy. At 0 we get 1. 1 is above the asymptote. And as soon as I find even one point that lives in that region, you know that your whole branch must be in that region. So you don't have to test 1 and 2 and 3. You just sketch the thing in. And I don't want to say that 100% of the time the other branch is sort of diagonal from there, but like 99% of the time that's true. But we certainly have seen examples where both branches are above the asymptote. But for a simple function, again, where the numerator and denominator are both linear, you can pretty much rest assured the other branch will be down here. But let's plug in -2, just to be sure. -2 gives us 1 over -1, which is -1. And lo and behold, yeah, we are right where we thought we would be. That's a really shaky graph. It's very hard for me to draw neatly on my little tablet thing. So just forgive my graphs, and you guys know what they ought to look like. But now that that's done, we can see that our range is going to be similar to our domain. It's going to be all real numbers except for the horizontal asymptote, which is at 0. We can see that for boundedness, we're not bounded. Our increasing interval is none. This thing is decreasing forever. But we're not decreasing at the actual asymptote. We don't even exist at the asymptote. So you'd have to give the decreasing interval as 2 separate intervals. So it'll be -infinity to the asymptote at -1, and also -infinity to infinity. Oh, no. -1 to infinity. And remember, it's not appropriate to use the U symbol here. You only want to use the U symbol for unions when you're talking about a set. And the only thing that is a set is domain and range. And if I had you solving an equation, if we said 1 over x plus 1 equals, I don't know, 10 or whatever, then the set of all points that makes this true is a solution set. You could say x is an element of the set that contains, and then you put your answers in braces. That's a set to solution sets, and for those you would use the union symbol. But for just listing intervals, I don't use it because intervals are different from sets. Extrema, we don't have any. We don't have mins because we go down to a -infinity. I can't really say this is a local max because the points to the left of it are still, of course, higher, right? So there's just no extrema, so kind of another boring one. Reb we're saving for another day. And for our symmetry, if we were just centering here at the point of intersection of the two asymptotes, then that's odd symmetry, right? That certainly looks like odd symmetry. But odd symmetry has to be symmetry about the origin. And since our graph has been translated left by 1, that little change does spoil our whole symmetry, right? I mean, if you fall back on the algebraic definition, remember f of x is supposed to be equal to the opposite of f of negative x, and we just don't have that. We can see it here, right? 0, or maybe negative 2 is the better choice. But if f of negative 2 is giving us negative 1, then f of positive 2 has to be giving us positive 1 if we're going to be odd. And just that quick test proves that we're not, because 2 is giving us 1/3 instead of 1. So this one quick counter example shows that even though we've graphically got something really, really similar to odd symmetry, we don't have actual odd symmetry. So this is neither. But of course, my little counter example, or appealing to the geometry of the function, none of that is okay, because I specifically said do it algebraically. So we've got to do it algebraically. So grab your function, plug in the negative, and just show me that it doesn't equal what it's supposed to equal. So f of negative x will be 1 over negative x plus 1. And if you, well, right away, we can just say, guess what, that's not the same as f of x, therefore not even. Technically, we're supposed to address both. Then if you try to simplify this by factoring out the negative 1, then you get x minus 1 in the denominator. This 1 negative in the denominator, we can just kind of factor out and have it apply to the whole function. So we now have the opposite of 1 over x minus 1. And then because it's x minus 1 instead of x plus 1, we can say that that is not equal to the opposite of f of x. Therefore, not odd. And finally, once we've proven that we're neither even nor odd, we're done. So that's it. That's number 8. And then number 9 should just be trying to make this a little more complicated. It's still a pretty simple function, but we're moving it up 1 in power. So it's now 1 over x squared. So how will that change our graph? I don't know, I didn't just make a graph that had axes built in. Just keep drawing the axes by hand. I would, if I were you, go ahead and plot points again, like usual. If I make a little t-chart and I plug in 0, then immediately we go, oops, that's undefined. And that's the only value of x where we're undefined. So we can go ahead and say, before we do anything, that our domain will be all numbers except for 0. Then plugging in 1 gives 1, but plugging in negative 1 also gives 1, which seems to be implying an even symmetry. Plug in 2, and you get 1/4. Plug in negative 2, and you get 1/4. And we're bumping into that issue again where my little tablet likes to connect the dots here. So when I go to make a 4, when I go like this, oftentimes it connects those two things, and I end up with something that can look like a 9. I don't want to have to fix it every single time, so hopefully you all will watch this video and hear me say that. Hopefully you'll all just know that 2 squared is 4, not 9. So this is just a trick where the pixels are lighting up when they shouldn't. Anyway, maybe one more pair of numbers will give me a sense of what's going on here. If I plug in 3, we see that we're getting even smaller. Now, oh, that's kind of annoying, because now I'm actually getting 1/9. That makes me want to rewrite this, but I'm going to not. All right, so what just happened? At 0, we were undefined, so vertical asymptote. At 1, we got 1, but at 2, we got 1/4. At 3, we got 1/9. So what you should be able to tell from there is we've got horizontal asymptotic behavior, where the graph is decreasing, but it's never going to go negative. It's never even going to get to 0. Even if I went all the way out to 100, wouldn't I just get 1 over, what, 10,000? So you get this number that's infinitesimally small, but it isn't 0. So you know you've got your horizontal asymptote at 0. And in fact, if you were paying attention, then you already heard me say in the last problem that as long as the denominator had the greater degree, which this one does, it's degree 2, and the numerator is degree 0, then you automatically have a horizontal asymptote at y equals 0. Any rational function whose denominator has the greater degree will have its horizontal asymptote right on the x-axis. So we should have known that. So what's happening here? Does this thing kind of bump up to some maximum value and come around? No. If you plug in another value like a half, then you get 1 over 1/4, which is just the reciprocal of a quarter, so it's 4. So at a half, we're up at 1, 2, 3, 4. If you plugged in a slightly smaller fraction, like 1/5, then you get 1 over 1/25, which would be 25. So we see the smaller our fraction, the greater the output is. So we've got a vertical asymptote, like you assumed. I assume, like you assumed, that we just get a branch that fits in there. And again, because this is x squared, we can't stick to that rule that the other branch is just going to be over here diagonally necessarily. In fact, we know that it won't, because when you square negatives, they come back positive. So we will get the mirror image of this over the y-axis. Our negative inputs gave us positive outputs. So we get a point here, we get a point here, blah, blah, blah. So we should see this graph mirrored over here, which again is classic even symmetry. Again, forgive my graph, it's really, really bad, I know that. If you really care, you can always go to Desmos and graph the thing yourself if you want to see a better looking version of it. Squared. The other thing you can do in Desmos, by the way, if you're feeling lazy, is if you want x squared, just literally do xx, right? I do that trick all the time. Even if you wanted like x to the 5th, you just go 1 over 1, 2, 3, 4, 5 x's, and then there's x to the 5th, right? But anyway, there's your graph. You can see that we've got it right. It's nice and smooth here, so we know that we've got that real even symmetry. I took the time to do this because those little inconsistencies in my graph, they do bother me. I don't want you to do them. So here, the fact that this graph bends around, I haven't been asking this, but it'll be on the quiz. I should be asking you if the given rule is even a function, like the vertical line test thing. And my graph is so sloppy that we don't even pass the vertical line test. That's actually kind of a big deal. So be careful. This should be yes. So just a little inconsistency like that can make your graph not a function. It can make your graph sort of not have the right symmetry that it's supposed to have. And all of that sort of telegraphs to me that maybe you don't really know what you're doing. And I don't want to have to worry about whether you're just a sloppy drawer or whether you don't understand math. So if the thing is sloppy, you might want to erase it and fix it. Okay, what is our range? We can see that our range is everything from 0 to infinity. But the 0 is going to get a soft bracket because it's an asymptote, not a solid point. We can see that because we've got that asymptote, we are bounded below. The left-hand side of our graph is increasing, so negative infinity to 0. But the right-hand side of our graph is decreasing, so 0 to infinity. Again, there's no extrema. So if anyone doesn't understand extrema, it's at this point maybe you've got to reach out to me for extra examples because we're just not seeing a ton of great examples. But there's no extrema. We're not going to do Leb and Reb. You do have to prove to me that this function is even though the evidence is quite strong. So you'll say f of negative x equals 1 over negative x squared. We've done the -1 thing to death, but maybe I'll do it again just to remind you that when you take your quiz, I'm not really interested in you guys taking shortcuts. I'd want you to really show me this. But this would become 1 over -1 squared times x squared. And at this point, the -1 squared can just become 1, essentially go away. You get your 1 over x squared, which is exactly the original function f of x. So therefore, f of x is even. So again, remember, it specifically says you must do it algebraically. So don't make an appeal to the graph. Don't show me data points, specific data points. You have to prove it to me generically. And that's it. So number 10, similar to number 9, but we're wondering what that -1 does to the graph. -1. We're wondering what that +1 does. This is still a rational function, so in terms of naming the function, this is another rational function. If I was going to graph it, then the big difference this time is the previous function had a vertical asymptote because the denominator had a 0, right? X squared was equal to 0 when x was 0. That made a vertical asymptote at 0. This function, though, if you grab that denominator, x squared plus 1, and set it equal to 0 to try to find the zeros, then of course you're going to subtract 1 from both sides. You're going to take the square root, and you're going to find that the only zeros are imaginary, plus minus, right? You get imaginary values, and imaginary values obviously can't be graphed on a graph in the real coordinate plane. So this graph actually does not have any vertical asymptotes, so it's going to be different from the other one. So we know our domain is all reals. And I guess we better do a little t-chart and just start examining how this graph behaves. 0 is going to give us 1. And if you plug in 2, you get a 5th. Why did I go to 2? I don't know. What do you get at 1? I'll squeeze it in. You get a half. Okay, and what's going to happen as we continue out? At 3 we get a 10th. At 4 we get 17th. So again we see that as the x's increase, the y's are getting smaller, but they're never going to go negative. We see that they're tending towards 0, so we should be expecting that we do have a horizontal asymptote. In our graph, if it starts at 0 and picks up those points, it's gonna go like this. There's a little more to talk about on the shape of this graph, but I'll wait. What happens on the other side? -1, well, you square it, you get 1. 1 plus 1 is 2, so it's still a half. So again, this seems to be implying even symmetry, right? +1 gives a half, -1 gives a half. It seems to be even. Keep going. If you plug in -2, you square it, you get 4. So yes, we get +1/5 again. More evidence that we are even. So I'm going to go ahead and sketch the other half of this graph. So the question is, what happens here? If you thought the graph came down like this and the other half came down like this, then the graph would have a very sharp point. But at 0, if the graph comes down like this, sort of like the top of a parabola, and the other half comes down like this, then you have a much smoother graph. This is the option we have. The graph does behave that way. These are sort of calculus ideas rather than pre-calculus ideas, but I'm going to just say it now because we have a good example of it. Looking at this part of the graph, you in the past have said it opens down. The more rigorous way to talk about that is to say that it is concave down. But then look over here. On the other part, at some point there's a change in the graph. Maybe that change is right about here. And suddenly now you've got a branch of graph that really kind of opens up. That's called being concave up. And this idea of being concave up or down generically is called concavity. So if I ever asked you about concavity, you'll know that I just mean which direction is the curve bending, so to speak. Are we concave down or concave up? And just to give you one more, foreshadowing bit of information, this point right here, where the concavity changes, is called a point of inflection or an inflection point. And this has become kind of a buzzword. You guys hear this all the time. Like in, I don't know, when they're talking about unemployment numbers or whatever. If the unemployment numbers had been coming down and down and down steadily, but then they start to come down slower and slower and slower, they say, ooh, the unemployment numbers are at an inflection point. They use that, which is kind of interesting. Anyway, that's way more than you really need, but I'm giving it to you anyway. We've got our graph now, so the rest of this should be cake. What's our range? We see it's 0 to 1, but we do not get the 0. Oops. We do not get the 0, but we do get the 1. So it's going to be soft bracket, hard bracket. For boundedness, we are bound below by the asymptote, and we are bound above by this maximum value at 1, so we are bounded. We have a left-hand side that increases, so that's negative infinity to 0. We have a right-hand side that decreases, so that's 0 to infinity. And we finally do have an extrema. We have an absolute max. That's at y equals 1, which means it's also a local max. But there's no other extrema other than that point right there. So for mins, you can say none. We are not going to do 11 reb. And again, we've got another function that certainly appears to be even, so let's just quickly prove that yes, we really are even. So the original function f of x is 1 over x squared plus 1. So what is f of negative x? Missed it. There we go. It would be 1 over negative x all squared plus 1, which means we've got 1 over. I don't know if I can be bothered to do it again, but I guess I better. I better model the work that I expect you guys to show. So you'll show me that negative 1. Then when you square that, you get negative 1 squared. That's why it goes away. You get an x squared and a plus 1. So negative 1 squared is 1. It essentially cancels out. And you get your 1 over x squared plus 1, which is exactly equal to the original function f of x. So, therefore, f of x is even. Why? Because f of x is equal to f of negative x. Okay. Writing with the mouse. Okay, great. I think that's just about it. I think oh no, there's a lot more. Okay, keep going. This should be a real piece of cake. This is called a constant function. It's just going to be a horizontal line. Dang it. What the? So it's just going to be a horizontal line at 2. So there's not a heck of a lot to talk about on this. But there's some little nitpicky things. So what's the domain? Pretty obviously all reals. What's the range? Some of you guys would probably be tempted maybe just to write y equals 2 and that's it. And that's fine. I don't think I'd be mad about it. But we did talk in class a little bit, although period 8 you maybe never heard this. If your range is just a finite list of outputs, then you typically want to list all those outputs and just put it into braces, almost like a solution set. So you'll say the range is really just the number 2. So you put it inside of braces and show it, and that sends the message that it's a finite list of possible values. Boundedness, we're pretty obviously bounded both above and below, so bounded. As a constant function, we neither increase nor decrease, so this will be none. Max, maybe the jury's out on this a little bit, but I say, if you look here, this point, is it the biggest overall? Well, yeah, there's nobody lower than it, right? So does it matter that somebody else also has an output of 2? It doesn't. If there's like a tie, if we had a graph like this that had even symmetry, you wouldn't say that these points aren't maxes just because there's another point that's at the same height, right? If this height here was a height of 8 you would definitely still say that 8 is the max, right? It doesn't matter that it occurs twice. So for that reasoning, this value of 8, there's never a value greater than that, so we should be saying that the max is an absolute max at y equals 8. And same with locally. If I build a window around this, is there anybody greater than him? Nope, then he's a max, a local max. So that's a little tricky. But based on the way our definition works, it's not about being uniquely bigger than everybody else. It's just about whether or not anybody's bigger than you, and nobody is, even when it's a tie. I don't know, I can't figure this out. Erase that. I don't know why I said 8 either. I confused myself with my example. 2, obviously 2. 2. And the local is also y equals 2. And then the weird thing is that that means by our definition we're also a min. We also have an absolute min at 2. And a local min at 2. And we do not have to worry about this. And I guess clearly we are even because we can be reflected over the y-axis. So to have to prove this, I guess it's easy. Because if f of x is 2, then to find f of negative x, if there's no x to replace with a negative x, then obviously it's still just 2, which means they're the same, which means therefore even. So the algebra here is really easy. You don't even have an x to modify, so you don't really have to do any work. You just show that f of x is 2 and f of negative x is also. So that's it. That's, for a simple equation. There was actually kind of a lot here to talk about. Moving on. So 12 is another cube root function, but it's got a quadratic underneath. So for that reason, when we ask you for the function name, I don't know what you're supposed to say. To me, it's not technically a cube root function. Cube roots should have linear radicands. I think we're in the gray area here. I'm not sure if it has a special name, so I'm just not even going to worry about it. What's our domain? Our domain should obviously be all real numbers. We've got an odd radical, so positives and negatives are fine. Then we also have x squared, which means even if we plugged in something negative, it would be turned into something positive before we ever tried to take the root of it anyway. So our domain is all reals. Our range, maybe you can tell, based on what I just said, that any negative input gets squared and turns positive. Then we go to take the cube root of it, and it's going to be positive. That seems to imply to me that we'll never get an output that is negative. All of our outputs are going to be positive, positive, positive. So that seems to imply that our range will be 0 to infinity, doesn't it? Now, do we actually get 0? Sure. Let x be 0 and you'll get 0. So it'll be hard bracket, soft bracket. For boundedness, this also implies we have no upper limit, but we clearly have a lower limit at 0, so we should be bounded below. Increasing, decreasing, I don't know. Let's see. Starting at 0 and going to 1, 2, 3. As the x's increase, what are my outputs doing? Well, we're getting bigger and bigger radicands, so the cube roots should be getting bigger and bigger. So it definitely seems like we're increasing. For the other side, as we decrease, when you square the -3, you get 9. That's bigger than this one, so it does imply we're coming down, right? We started bigger, and we're getting smaller. So it seems like we decrease, and then we increase. And the change would be at 0. So I'm ready to say, even without a graph, notice I'm trying to do this without a graph this time. I'm trying to say that we seem to increase from 0 to infinity. We seem to decrease from negative infinity to 0. This does seem to indicate that maybe there's a minimum value at 0, and the output there is 0. So since we hit the origin since we decrease to it and then increase, seems to imply there's a absolute min that is y equals 0, and that would mean there's a local min there as well, which is y equals 0. Maxes, I would think we don't have one, because it seems like we grow without bound, and we grow without bound, so I'm going to say none. And then let's actually graph this thing, see if I'm right. So again, we could just go to Desmos for that. So to get to the cube root, I mean, you got two options. Hopefully y'all remember that one way to get a root is to just use a power. If you do the reciprocal, then the 1/3 power is the same as a cube root. And then for x squared, we can go xx, which is the trick I showed you, or we can go x squared. But there's our graph. It's not exactly what I drew, is it? But that's okay. If you wanted to do this right, by the way, then the only way to get higher order radicals, you can't get it here. This is a dedicated square root button. It can't be turned into a cube root. To get a cube root, you got to go over to functions. It's in miscellaneous, and then you see the nth root, and that gives you an option to modify the index number of your radical. So now you can go x squared. Anyway, there you go, same graph. So my graph is a little bit wrong, which is fine. The only reason I'm wrong is because of my concavity. I showed us growing in a way that was concave up. We were growing increasingly faster and faster, when we actually should have been growing fast at first and then slowly. So the difference there is concavity, which I mentioned before. This one should go that way. So that's what you get, basically a graph that, if you go back to kindergarten, looks like the way you used to draw birds back in kindergarten. Oh, come on. See the birds flying over a beach? That's what our graph should look like. Okay, get rid of that. So how would you know that, by the way? How would you know the concavity of the function? I don't know. You could stop and think about it, I suppose, much more deeply. You could plot points, a lot more points, to sort of see how the graph increases, whether it's increasing faster and faster and faster, or slower and slower and slower. I don't know. Maybe it would make sense to you that the difference between the cube root of 1 and the cube root of 8, let me actually write this out, see if this makes sense to people. Cube root of 1 is 1, but the cube root of 8 is 2. So with an increase of only 7, we increased by 1. Now think about going cube root of 27 is 3. But you got to go all the way to 64 to get a cube root of 4. So suddenly, for larger values of x, that increase of 1 in your outputs corresponds to an increase of whatever 64 minus 27 is. I don't know. 30, 37? Yeah, that's a big difference from 7, right? So clearly now, to get the same increase in y values, you need a much greater increase in x values. So that seems to imply we grow quickly at first, and then less quickly over time, right? Here, it took me 7 units to increase by 1. Here, it took me 34 units, 37 units, whatever, to increase by 2. Maybe that gives you some idea. Again, what I'm talking about right now really is calculus, talking about the rates of change of the function. But sounds like it's something that would be good to know, doesn't it? Okay. So anyway, I'm overthinking and over-explaining, but I think everything I'm saying is good. So we know we've got the point 0, 0. We know we've got the point 1, 1. And negative 1, 1. We've got the point... There's like nothing else that's actually clean. I guess 64. So if we went all the way out to 8, then 8 squared is 64, and the cube root of 64 is 4. So that's a nice integer valued point. So that's here. 2, 3, 4. So that's here. So there must be another nice integer value here. How would we get 3 Cube root of 3 is 27. Nope, but there's nothing that clearly squares to 27. So I think these are the only real points. But, you know, with those points plotted, now you can definitely see that the curve should be concave down. And we should be getting that shape. Again, forgive me for not hitting my points. If you are taking a quiz, you would erase and try again, right? And in fact, no, I'm not gonna, but you guys will. Anyway, there you go. We certainly look even to me, so let's prove that we are even. We'll say we gotta just do f of negative x like we always do. So this will be the cube root of negative x squared. So that's the cube root of negative 1 times x all squared. That's the cube root of a negative 1 getting squared. And again, negative 1 squared is 1, so essentially now we can have that go away and land right back on cube root of x squared, which is our original function f of x. So we've done it. We've proven that f of negative x equals f of x. So we can say, therefore, f of x is even. Again, be super cognizant of the fact that we are straight up asking you to do it algebraically. You cannot say it's even because we have reflectional symmetry over the y-axis. That is a geometric argument, and you won't be given credit for it. Now, does that mean there'll be another question on the quiz that says, justify your answer geometrically? Yeah, maybe. If that question was there, you would say f of x is even because. Ah, crud. Okay, so if that question was there, you would answer with the symmetry. You would say f of x is even because. It has symmetry over the y-axis. And obviously, if you were trying to justify odd symmetry, you would say f of x is odd because it has symmetry over the origin, or about the origin. And you don't have to explain that. I'll assume you know that symmetry about the origin means it's got that 180-degree rotational symmetry, or it's got that two-fold reflectional symmetry. We have to reflect over the y-axis and then also reflect over the x-axis. But that should bring us pretty darn close to the end. So yeah, we get to the optional. Feel free to just turn the video off right now if you want to. But I am going to do my best to actually try this problem, because there will be stuff kind of similar to this. So on we go. What's our domain? I see a cube root in the numerator, and cube roots don't care about negatives, so that doesn't add anything to our discussion of domain. But I do see division, and I do see that the 0 of the denominator is 0. So I'm thinking our domain is going to be all reals, except for the number 0. And that 0 should manifest itself in our graph as a vertical asymptote. So forgive me while I draw these axes. So vertical asymptote at 0. Okay, cool. That's something. That definitely helps me to shape my graph. What else can we tell by investigating this closely? XY. 0 made us undefined, but at 1 we would get 1 plus 1 is cube root 2 over 5. So I don't even know what that is, but it's small. I don't think we can do this, right? I mean, we have calculators, so we can boil this down to a decimal, but are there nice, clean, integer valued outputs that we can solve for? I kind of don't think so. Cube root. No, this is just going to always be ugly. So what can we do? Will this ever be negative? Yes, because plugging in -1 right away gives us -2. Yeah, -1 plus -1 is -2, all over -5. Oh no, that comes out even, doesn't it? Because we would have essentially negative cube root 2 over -5, which is going to be the same thing. So actually, I'm starting to think this will have even symmetry. Try 2 and -2, see if that still bears out. You get 8 plus 2 is 10, so cube root 10 over 10. And if you plug in -2, then -8 plus -2, -10, so negative cube root 10 over -10. Yeah, so that even symmetry seems to work out. Again, that was only a numerical approach. We'd have to prove it algebraically. As far as the range, from what I just explained to you, this numerator will be positive for positives, and the denominator will be positive for positives, so that's all positive outputs. But the numerator will be negative for negative inputs, but the denominator will be negative for negative inputs too, and a negative over a negative is a positive. So that seems to be telling me that we will never ever get a negative output, so my range definitely seems to be 0 up to infinity. Now, are we growing as we grow? Root 10 over 10. You'd want to take out your calculator and evaluate what is cube root of 2 over 5. Let's just say this is 1 over 5-ish, so it's like 0.2-ish. Cube root 10 is like 3-ish divided by 10, and that is like 0.3-ish. So we do seem to be growing. As the x's grow, the y's seem to grow. So it does seem like we go from 0 to infinity. Do we ever get 0? Nope, because the denominator can't ever be 0. The numerator won't ever be 0 either. So I would say soft bracket. So what I'm not liking here is the rate of growth. The function's doing something. Okay, I don't care. I kind of want to just cheat. I shouldn't cheat. Let's keep going. We should be testing some other value. Going from 1 to 2, I'm kind of comfortable saying that yes, we increased. But we should be looking at numbers like 1/2 and -1/2 as well to see what's happening between 0 and 1. Because I wonder if we got that asymptotic growth, or I wonder if we just start at some max and decay down, whatever, or increase. So plugging in 1/2 would be what? 1/8 plus 1/2, which is 4/8. So 5/8. So cube root of 5/8 over 5/2. What am I? I'm supposed to know what that is? I could use my calculator and figure it out. So maybe I will. Cube root of 5/8 divided by 5/2. Ugh. Where's just the regular graphing calculator? I mean, calculator. All right, there's the cube root. Then I'm dividing by whatever we said. 5/2. So you just multiply by 2/5. So something small. Dude, I don't know. I'm a little puzzled. Okay, let's graph the thing. I quit. So what are we doing? Cube root of x cubed plus x, but all over 5x. Oh, I don't like that one bit. Okay, duplicate this by clicking this. Boop. Turn it into a table of values. Boop. Clear out this garbage. I just tried to do a half, didn't I? So I screwed it up? That stinks. Okay, I screwed it up. My bad. But yeah, there's a half. Here's 1. Here's 2. So I was off. My calculations and my math were off. But this is our graph. Glad this was a challenge problem. So don't sweat anything quite like this. Okay, whatever. If we did negative a half, you see we get that symmetry. I was right about the even symmetry at least. -1, -2, plotting those points, those mirror images, we definitely see that even symmetry emerging. Yeah. Okay, if you zoom in too close, you could definitely start to think that maybe you've got a horizontal asymptote here at like 1/5. Now, do we? I think we actually do, right? If I go out and out and out, the further out I go, you can zoom way out, move way over to like 500 or whatever, zoom way back in. I went too far. Where the heck's the graph? Oh, I'm way too far. Okay, but yeah, there's your evidence. That is 1/5. So our horizontal asymptote's at 1/5. So I did make another mistake because I think I said would be asymptotic at 0. But again, to explain that away, it is 1/5 because of the 5 here. Now, to really explain that algebraically, I'd have to go deeper than I want to go into. In the next few lessons, when we talk about limits, we might get into this, but we could take the limit of the numerator as it grows, take the limit of the denominator as that grows, and then kind of come up with it. But it does sort of make sense that the coefficient on this is 1, coefficient on this is 5. So the limit to our growth ends up being 1/5. So I don't know. Is this worth talking about, or am I confusing you more? Probably confusing you more. But the range should be 1/5 to infinity. Would have to make that change. Okay. I can confidently say that we're bounded below. And that we are increasing from 0 to infinity. Oopsies. -infinity to 0. And decreasing from 0 to infinity. For maxes and mins, we're not going to have any because we saw that branch going up, up, up. This branch is coming down, down, down. So we're bounded below at -1/5, but or +1/5. The 1/5 was an asymptote, so it can't be our min. Infinity seems to be our max, which can't be our max, so this is none. And we've got that even symmetry. It is important that you could do this algebraically, so I'm going to do it algebraically. So given that that's our function, we already know we're even by sort of investigating the graph graphically and numerically. So algebraically, what's f of -x? We have to turn all the x's into -x's. So you get a -x cubed, you get a -x. That's all over 5 and a -x. So what's going to happen here is up here we can factor out the -1 like we always do. And both of those factors get cubed. Here you can factor out a -1. And that's, you know, kind of a weird way to do it, but I'm thinking ahead to what I have to do next. Maybe just here too, I'm going to factor out the -1. So it'll be a -1 times a 5x. So I did this like this because the -1 cubed is -1. Now -1 is now a common factor. So you can factor it out under the radical. You now have -1 as a factor, as a coefficient on x cubed plus x. And notice that's the original radicand. And then downstairs you've still got this -1 hanging around. And you're going to leave that guy hanging around because in a second we're going to factor this -1 out of the cube root. We're going to do that by splitting the cube root. We can just do the cube root of the -1 and do the cube root of the x cubed plus x. So again, we're using that property that says any root of a product can just split. It can be the nth root of the A multiplied by the nth root of the B. Very important property of radicals. It holds true for even and odd radicals. So we're using that here to take the cube root of the -1 separate from the cube root of all this other stuff. And then this is all over -1 times 5x. So maybe you can see where this is going. Suddenly, the cube root of -1 is -1. So our numerator now has a factor of -1. In our denominator, there's always been a factor of -1, just patiently waiting down there to cancel. And now it cancels. The -1 and the -1 cancel, giving us our original expression, cube root of x cubed plus x all over 5x. So we can now say that's the original function f of x, but it was also -x, therefore f of x is odd, even. There you go. Okay, so we did it. We're not doing this. All right, forgive me, kind of floundered on that problem, but I think the floundering was good. Thinking out loud can kind of show you the thought process. Even when the thought process is wrong, there's some value to it. So anyway, if you guys sat through this, then you're champs. This video seems like it's going to be about an hour long, so my apologies. Anyhow, I'll see you Wednesday, and we'll review everything. Bye.